All right. Hey, everyone. It's Matt. I want to talk a little bit about discrete distributions today. But first, it might be worthwhile to talk a little bit about distributions in general. So we have to define this notion of a random variable. This is some sort of function that's assigning values to the possible outcome in a particular experiment. We can consider some examples here. There's a few below, but let's put another one up here. We may have x be the value on a single die roll. So we roll a die and we get a number. X here can take a number of values. The value is 1 to 6. So that's one example of a random variable. Two more examples below here. We have x1 is time to failure in minutes of this particular CPU. And x2 could be the number of BCIT CST graduates who know how to build circular linked list data structure among 6 randomly selected students. So you select 6 students and want to know how many among them can do this particular task. So as we said, there are 2 particular kinds of random variables. There's discrete and there's continuous. Discrete is a lot like the second example here. So it is having either a finite number of values or countable number of values. So it could be infinite. You could have infinitely many, but they would have to be countable. So 1, 2, 3, 4, 5, and so on. On the other hand, a continuous random variable can take any value sort of between 2 values. There are sort of no gaps. This is kind of like the real number line or something. So in the above example, you can imagine that x2 is discrete. So this is countable. We can have these values here, and we can count them. We can include 0 here. We could have 0, no, and we could have or 1 through 6 may know. These are the possible outcomes. It's discrete. There is countably many. On the other hand, the first example was continuous. You can imagine having any particular value on the positive real number line. So we could have any value between 0 and infinity, and to any level of precision. You could imagine having some long decimal be the result of this question, and we could have as many decimal places as you might like. Okay, so a probability distribution is what we'll go to next. This is going to give the probability for each value in the random variable. So the variable has a number of values, and each value has a particular probability. So let's consider the example we were thinking about earlier. Let's take these students and see if they can construct this circularly linked list, considering 6 total students that we select at random. So x here, it's a little x here. We may often use big X though. For the variable, it has these 7 options here. Each of the 7 options is given a particular probability, denoted by p of x. Most common probability is maybe 1, with 6 being incredibly unlikely, so much so that we think it's basically 0. This 0 plus means it's not actually 0, but it's so small that we can't resolve it with our current level of precision. So this is just something that's less than 0.001, which we're rounding to 3 decimal places here. So this particular probability histogram here is displaying for us the probability of a certain subset of these 6 students that we pick, whether or not they know how to do this task. So it's a lot like the histograms we've seen already, except the y value here is actually giving us probabilities. We may notice here the relationship between probability and area. So since each of these boxes has length 1, the total area in one of these boxes is the same as its y value. And of course, more area here, more area coming here, means there's a higher probability. So one of the CST grads knowing how to do this is the most probable outcome. Not being super kind to CST here. Okay, let's keep going then. There are a few requirements if we're thinking about probability distributions. So first of all, we will need this first one here. This is saying that the sum of all possibilities is 1. We can think of this in the intuitive way where if you round up all of the different possible things that could happen, the chance of one of all of the possible things happening should be 100%. The chance that something will happen is 100%. We expect that something will happen. So that's the first one here. We need to have that be true. Otherwise, we're missing something. Otherwise, there's some possibility that we haven't accounted for. The second rule here, we can also think of this in the intuitive way that percents should be between 0 and 100. So you can't have negative percent, you can't have more than 100%. Neither of those two things will make sense. So if we have these two satisfied for a particular distribution, a particular discrete distribution, then we will call it a probability distribution. Now, we can, much like when we were working with data in descriptive statistics, we may wish to understand different properties of the probability distribution and may wish to calculate things like mean, sometimes called expected value, or variance, and correspondingly standard deviation. So as before, we have mu and sigma squared here. These formulas, I can tell you, will appear on formula sheet. Formula sheet. But you should be perfectly able to use them. So the mean here is also called expected value. It's kind of the most likely thing, or the thing that we kind of expect to occur. It's the average. Standard deviation here can come by taking square root of the variance, which is defined in this way here. Let's go now back to our example and think about computing these things for each of mean and standard deviation. So for the mean, the formula says to add up all of the x's times all of their particular probabilities. So the first outcome, the first x that we had was 0. Maybe 0 students know how to do this task. And the corresponding probability was about 26%. We can add to that the probability that one of the students knows how to do the task times its corresponding probability. And we can keep going here, adding 2 with its probability, 3. Probabilities are getting smaller now. By 5, they've all but disappeared. and 6 will just multiply by 0. It has such a small probability. So one can compute this thing out, and you get about 1.2. And so the way you think about this is that in a randomly selected group of 6 students, CST students, you expect that about 1.2 will know how to do this. So that's mean. We can also try for the variance, which is related to standard deviation. Variance. Now, you may notice there are 2 formulae up here. So there's the computational and theoretical. The theoretical is maybe the one that may make the most sense. So you may recall defining standard deviation as some kind of distance of all the x's from the mean squared, and then some kind of averaging, much like averaging up here. We're multiplying by p of x and taking the sum. One can derive this thing, but will take us a little too far afield to do that. So let's be content with this formula here. One can do a little bit of algebra. It's not hard, but again, it would take us a little too far afield. To put it into this more convenient form, the two are equal, they mean the same thing, but the computational one is a little bit nicer when you actually go to compute things. So let's use that, given that we want to compute. So it's similar to before. We can take all of the x's and square them and multiply them by their corresponding probabilities. So it's looking a little bit like the line above, just with some squares. .082, 0.015, 0.002, and finally 0. Now we've added up all of the products of the squares with their probability, but we also have to subtract off the mean squared. So you need the mean in order to calculate variance. This should be squared here, sigma squared for variance. We have to subtract off the mean squared, so we need to have that already. If one computes this out, you get about 0.96, this number here. And if we take the square root of that, then we can get the standard deviation. Now, having both the mu and the sigma, much like before when we were thinking about descriptive statistics, can tell us how to judge different outcomes, whether they are unusual or not unusual. So we're going to play the same game that we were before to determine whether something is usual or unusual. So in this example above, we may have the question, we may wish to know if it's unusual to find 3 of these students who know how to construct circularly linked lists. We can play with the Z scores, much like we had earlier. So recall our formula here for Z score. We have already the mean. Let's provide it here. We'll do a little bit of rounding. And we can find the standard deviation by means of square root. It's close to 1. It doesn't change so much. And our query here is 3. We want to know if 3 is unusual. So let's put x equals 3 in here. Equals. So let's do some subtraction and division to find the corresponding Z score of this query. And we get a value of about 1.8. So using our previous rules, where we kind of select 2 sigma above and 2 sigma below as being our tolerance for usual versus unusual, in this case we would say that if one were to find 3 of these 6 graduates who know how to complete this task, you would say this is not unusual. So since our z is between -2 and 2, it is not unusual to find 3 of 6 students that can do this. Good. Okay, so let's keep going here. We've got another example to think about expected value, and this one will involve the game of blackjack. So in the game of blackjack, the dealer who you're playing against has 2 cards. One of the cards is face up. So for us here, the dealer is showing an ace and has a second card that is hidden away. If that other face down card happens to be a 10 or a face card, then the dealer will have what is called blackjack. So if the dealer has this ace and perhaps the other card is also a 10 or a face, then they will have blackjack, in which case you will lose. So we are kind of asking, if that other card down there is a 10 or face, we lose. But the players are offered the chance to make a side bet called insurance. One can wager up to half of your bet that the dealer has blackjack. And so if the dealer does in fact have blackjack, even though you lose the main bet, this side bet may pay you out at a rate of 2 to 1. Let's go through and compute some things here to figure out whether or not this is a good idea, whether or not we should take out some insurance. So we can think about the expected profit. So that's mu here, the mean, on this bet. And let's remark that we're using a single deck here, so a standard deck of 52 cards. Casinos often use multiple decks, which makes this kind of computing less doable, and so they always win and we will lose. But let's play this one now. So let's think about x to be the profit. That's the thing we're interested in on our insurance bet. Now there are a few possible outcomes. Let's say we've made a bet of $5. So either we will not win and we will lose the $5 if the dealer happens not to have blackjack, or if the dealer happens to have blackjack and our insurance pays out, it will pay out double. So we'll get x equals -5 or 10, and they'll each have some corresponding probabilities. So if we lose, our probability that x will be -5 here, we know already that one of the cards is out of the deck. It's an ace. So of the rest of the cards in the deck that are possible to form the face down card of the dealer, there's 51 choices left. All of the cards that would make us lose this bet if the dealer doesn't have blackjack would be everything except for the 10s and the face card. So all the remaining aces, all 3 remaining aces, plus all 4 2s, all 4 3s, all 4 4s, and so on. If you count all those things up, you get 35. And so our probability here is 35 over 51. So let's denote this is the proportion of cards. That are not 10s or faces. We can also do the other one here. So if the dealer happens to have blackjack, our insurance bet will pay off. The probability of this happening is, well, all of the tens and face cards together. There's 16 of those. Tens, jacks, queens, kings. There's 4 of them. 4 each is 16 over the 51 left. So this probability here is the proportion of cards that are either tens or face cards. Tens or face cards. So we can compute the mean by taking the sum of the product of the x's with the p of x's. There's only 2 here, so it's not so maddening. Plus 10 times the second probability, 16 over 51. If you crunch that out, it comes out to a big minus 29 cents. So it's pretty close to even, but if you play this lots and lots of times, you'll lose. You're kind of expecting on a given hand to lose about 29 cents. So maybe the insurance bet in this particular case is not such a great idea. However, you also have some information. So you have some cards. You're playing the game too. Maybe say you have a 3 and a 4. And maybe the player next to you shows you her hand. She's probably not allowed to do that. And you see a 5 and a 7. So now you know that there are these 4 non-face cards that are out of the deck. This will change things a little bit. Let's write that down. So we know an ace is out of the deck because the dealer's showing an ace. There's also the 3 and 4 are out because we've got them in our hand. 5 and 7 are out because of your friend. So these cards are out of the deck already. Let us now recompute the probability. So we might lose with some probability. We've removed 4 cards that weren't there before. We had already taken account the ace, so that drops us down to 31. There's also less cards to pull from the deck, which moves us to 47. We can do same for, for winning. Hopefully one of them is positive. So we can have 10 here with some probability being 16 over 47. So let's go ahead and compute the expected payout. Or in other words, the mean. Again, similar to before, with these slightly different probabilities. You crunch this out, and this one actually comes out to a positive 11 cents. So if you happen to know that your cards aren't face cards, and that your friend's cards aren't face cards, then the probability of the dealer having blackjack for a single deck is a little bit higher, and this is a reasonable bet. You play this lots of times and you'll win 11 cents on average per game. The casinos use multiple decks, and so you can't really do this, and so you lose money, so don't gamble. But I'm glad we got a chance to compute this here. So that's for general discrete distributions. There's some specific kinds of distributions we would like to talk about. The first one is the binomial distribution. So this one arises, as the name implies, when there's 2 outcomes, binomial. So you're doing some kind of experiment, and the result is either kind of a 1 or a 2, or a 0 or a 1. Somehow it's either win-lose, live-die, true-false, success or failure. You may hear these sometimes called binomial experiments, or maybe Bernoulli trials. There's a few common features of them, and so the first one is here. The other three are on the other page. These are something that these features are something that one should check to make sure these requirements are met. So the first one here is that the experiment will consist of identical n number of identical trials. So you're repeating some kind of experiment over and over again n times. That's the first one. The second one here is that each trial can have only two possible outcomes. We usually say success and failure. Two possible outcomes. Both outcomes might be good, both outcomes might be bad, but we normally just denote one S and one F anyway. The trials themselves should be independent. So your whatever happens on your first trial should not should not impact the outcome on the second or any subsequent trials. And the probability of success, S, which we normally call P, should not change from each trial. Similarly, the probability of failure of F, which we normally denote the probability of failure by Q, that should be the same on each trial. P and Q don't have to be the same as each other, they just have to be the same as themselves in each trial. Same probability in all trials. So let's think about this example of flipping a fair coin. We can note here that actually the coin doesn't really need to be fair in order for it to be a binomial distribution, but let's run with this fair coin first to see what's up. Let's verify the requirements. So the first one is that we have identical trials. So here we are flipping the coin 10 times. So n equals 10. We're just flipping a coin. Each coin flip is identical to the next. So that's satisfied. We have 10 identical trials. For the second one, we wish to know about the possible outcomes. There's two possible outcomes for this coin. We can denote either of them as success. Let's maybe call heads success and tails as failure, although there's no real reason to do this, but one for each, two outcomes. That's fine. The third option here is that each should be independent. It's true that coin flips are independent. Believing that if the coin comes up 10 times heads, believing that the 11th will not be 50-50 is the gambler's paradox. Don't gamble. And 4, the probabilities are the same in each trial. So the probability of success, often denoted by little p, is a half. We're flipping a fair coin. And the probability of failure, often denoted by little q, which can be computed using 1 minus p. The 2 should add to 1. This one is also 50% chance here. These probabilities could be changed. If it's not a fair coin, if it comes up 75% chance heads, then p just changes to 0.75 and q just changes to 0.25. Still a binomial experiment because each coin flip has the same possible outcome. If you modify the coin in between trials, then it's no longer binomial. You're messing with the probability. We have the following convenient formula when we are thinking about probabilities for binomial experiments. Because they satisfy so many properties and are so restrictive, we can compute in general this formula that you can use to find probability of different number of trials. We see here we're using the NCX, the combinations, so somehow we'll need to include a little bit of combinatorics, as well as probability of P and probability of Q's to some powers. I'll make a quick note to say that sometimes it's denoted in this way, B of xn p for either binomial or Bernoulli. You may be using this kind of notation and using this kind of formula on the quiz. So we can look forward to that. Let's see a couple of pictures here on the next slide. So here are some examples of different binomial density distributions. These are each for different kinds of coins, different sort of fairness of coins. So here's the P 50-50. So this here is a fair coin. Fair coin. Whereas this coin over here has little p equal to 0.1. This is a very not fair coin. We're doing each of these experiments 100 times, and this x-axis here is the number of heads that come up for sort of 100 trials, and the distribution here is where is how likely the number of heads to come up are. So you can see with this probability of 0.1 or 10%, 10 out of 100 here is the most common option, with the options beside it also coming up sometimes. We have 25% here, 25%. We've got the fair coin here is split right on 50-50. And this 75 here, maybe this is a coin that's weighted in favor of heads. We've manipulated it in order to succeed more often. So this weighted coin comes up heads 60 or 75% of the time. And the numbers here are clustering around 75%. So that's a visual description of these kinds of probability densities. We can also have some computation and compute using that formula that we just saw on the reverse. So let's take a look at this example. Let's think about the probability of these randomly selected students. Again, knowing how to construct a circular linked list. Perhaps we know that the probability is about 20% of picking a random CST graduate. Now, we may wish to select 6 total, and we are interested to know the probability that exactly 2 will know the method here. So this is a binomial experiment selecting a graduate with a 20% chance of, I guess, success and an 80% chance of failure. So we can repeat this binomial experiment 6 times, and we'll figure out how much probability there is of getting exactly 2. So as we say, n here is 6 total trials. The probability of success is 0.2, 20%. Q is always 1 minus p. For us here, it's 80%. And so we can use our formula, the probability of getting exactly 2, or sometimes written in this way, b of 2, 6, and 0.2. That will be 6 choose 2, p to the power of 2 here, and 0.8 to the power of 4. We can compute 6 choose 2, sometimes written in this way, using our familiar formula, 6 factorial over 4 factorial times 2 factorial. The 4 factorial will knock a lot of things out, so we just get 30 over 2, which is about 15. So 6 choose 2 is 15. We multiply by these numbers here. When one crunches this out, you can achieve see about 25% chance of this happening. So let's summarize. We've got 24.58% chance that exactly 2 will know. Okay, that sounds fine. This is one kind of question you might have, exactly 2 will know. But you may also have a question about maybe at least a certain number knowing. So you may wish to find the probability here that at least 3 will know. Now again, we have n equals 6. Our x here is a range now, or a collection of different outcomes. So we could have x equals 3 or 4 or 5 or 6. We could go and compute the probability of exactly 3, the probability of exactly 4, the probability of exactly 5, and the probability of exactly 6, and add them all together. That would be one way to do this. We would use the formula once for each of them, and then add them all up as such. A slightly faster alternative here will be to flip it on its head using complements as we've seen, to instead take 1 minus the probability of getting less than 3. That would be either 0, 1, or 2. So we're reducing the number of computations we have to do, which is a handy thing sometimes. So here's 1 minus the probability of 0 minus the probability of 1 minus the probability of 2. And in fact, we've already computed. So in part A, we already computed the probability of 2. So we actually just have 2 things left to compute, just 0 and 1. So I prefer this one here. It's slightly less work. So we can be happy about that. So for each of these 2 new ones that we haven't computed, we can use the formula 6 choose 0. 0.2 to the power of 0 and 0.8 to the power of 6 for the first one. For the second, we'll subtract 6 choose 1. 0.2 now to the 1, 0.8 to the 5. And rather than compute the last one, we already have done it previously, so let's just record the number here. At the end of the day, we can compute a few numbers for this. 3932, and then our familiar one here. This all comes out. Once we subtract them from 1, it's getting smaller to a little under 10%, 0.0989. So at the end of the day, there is about 9.8% chance, 9.9% chance that at least 3 will know. So not that much. It's a bit unlikely. Okay, so we'll stop there. We'll pick up here in class.